Start the recording. Okay, before we get into the chapter 2, I'm going to be here Thursday afternoon at the same time we did lab last time. And I'm going to go through the Microsoft Excel for chemistry. Whether or not you show up is voluntary. You're not going to be counted off for not being here. And the session will be recorded. If you want to come and zoom in, there's a link for 103 set up. So you can zoom in for that. And I'm going to be using Microsoft Excel, of course, so I can share my screen. But if you want to work along with me, you need to figure out how to be able to see mine and do yours at the same time. And I think if you take the screen out of full screen, then you can shrink it to one side and do the same thing for your Excel and work on your Excel at the same time. So it'll make a whole lot more sense if you're working along with me.
You could do it off of a phone, have Zoom on the phone, and then just work off your laptop or desktop.
That's fine. I was going to suggest if you have two computers, you can do that. I've got my work laptop right here that I'm interacting with you guys, and I've got my PC sitting right next to it, so I can do stuff over there if I need to.
Mr. Blah, the Microsoft 365, has anybody else had any problem trying to add that on and sign on into that?
I don't know. Response from the class? Anybody else have
I did
trouble?
at first, but then I figured it out. My password is just slightly different than it was for my email to originally sign on it.
Okay, who's talking? Was that Yesenia? Talking?
Yeah.
Okay. Okay, and who asked the question at first?
Jeannie.
Jeannie, okay. Are you still having trouble?
I am. I tried signing on, and I keep using my password for my email, but it just keeps kicking it out. And it told me to contact the, I guess the head ones. I didn't know exactly who I would get a hold of to find out how to do that.
With, you mean New River IT or with Microsoft?
I'm guessing it's connecting in with New River, because we had to put in New River as the school, and then we had to go in and put in our email address, and we were supposed to put in the password, which I put in my password for my email, and it's saying it doesn't exist.
Maybe it doesn't want that password. Does it want a new password? You don't already have an account with Microsoft, do you?
It's saying I do have an account.
Okay, so it's looking for the password for that account, not for your email.
Okay.
If you go on Microsoft and there's the option to reset your password, that might be a good option to take.
Okay.
It might fix the problem quicker than waiting for somebody to get in touch with you.
Okay.
That's what I try.
All right.
Okay, so that's what we'll be doing on Wednesday afternoon. I'll go through the Excel. Now, the rest of the labs, I've started making videos, demonstrations in the lab space. The first couple of ones, I think I make lab videos in the lab space at New River. And I also do the same labs, some of the same labs for Southern. So when I make videos for Southern, I'll just link them into your account, and it's the same material. It's just it's a different lab space. It won't look familiar, unless of course you've never been to New River, our New River lab, and then it doesn't matter. But that's how I'm approaching. I'm doing a complete demonstration of the entire lab in a video, and all you have to do is pay close attention so that when I generate numbers and data and observation in the video, that you're prepared to copy it down, because you'll need that information to write the reports. Okay, so let's get started with chapter 2. I'll try to get through chapter 2. Past semesters, I haven't been successful, even in the classroom setting, to get through the entire chapter. But as always, if you have to go at the end at 1:45, that's fine. I'll keep talking and make the recording, and you can pick up the parts you missed later. Okay, so I need to share a screen, and it'll be this one. And I'll start the slideshow. There we go. All right. So this is chapter 2. And it's on atoms, molecules, and ions. So what does that mean? Well, we're going to start getting into real chemistry now, but we're going to go way, way, way back into ancient Greek history. The ancient Greeks were the first to actually make an attempt to explain why chemical changes occurred. They missed the boat by a long shot, but at least they made an attempt. And they talked about the 4 fundamental materials in the universe, like earth, wind, fire, and let's see, earth, wind, fire, and one other one. But they got the ball rolling. And then during the Middle Ages, there was a fascination with changing one substance into another substance. And that the type of people that generally worked on those problems were, they called them alchemists. And some people like to say that they wanted to turn lead into gold. Well, some of them probably did. But some of them were searching for the elixir of life. You know, what would sustain life indefinitely. And in the process, they discovered lots of things, but it wasn't organized in a way that we normally think of science these days. They discovered some elements, and they used a number of different mineral acids, like sulfuric acid or nitric acid or hydrochloric acid, to investigate the various properties of the substances. It wasn't until the mid-17th century with Robert Boyle that modern chemistry started to congeal. And Robert Boyle, in fact, is often considered the first chemist. And what they mean by that was in the modern sense. He conducted experiments which were quantitative. That is, he got numbers for the things that were happening. And he also came up with the first experimental definition for an element. Now we know that an element is any substance that, when subdivided by physical and chemical means, reaches a point where it cannot be further subdivided. Now, how do we know? We know that it's not further subdivided or broken apart, so to speak, because all of the properties of the substance before and after the process are exactly the same. Now, that doesn't mean that some mistakes could be made. We could say, well, it didn't change when I did that experiment, so it must be an element. But that's the beauty of modern science. You publish your work. Originally, it was in Latin. And then other languages came in, and you disseminated your work among other scientists, and they investigated your results. They may even duplicate your experiment and see if they can shoot holes in it, or discover where you might be wrong. It's another word for that is peer review. So your peers in that discipline are looking at your work and giving it a critical eye to see if they can find anything wrong with it. And ideally, we still do that today. Okay, so in the process of the development of modern chemistry, several laws came out of investigations. And remember the difference between a law and a theory. A law just says what happens. It says, if these are the conditions, then this always results. If you change the conditions, then, okay, as long as the law is invoked in those conditions, then you can say this will happen. Doesn't say anything about why. We can't explain the underlying reasons or causes for why the law works. But the laws came first. And one of the most important ones, the first one, was by a Frenchman named Lavoisier. And his was the law of conservation of mass. And basically what he said was that during a chemical reaction, you cannot create or destroy matter. The mass remains the same before and after a reaction. That was pretty significant finding. And it's going to be made use of later. In fact, it still holds true today. Proust, who was another Frenchman, came up with the law of definite proportion. And all Proust said was that for a given compound, it's composed of two or more elements, and the ratio of the masses of the elements that are in the compound are the same, no matter what the origin. So if we have something like, say we have those two elements, and say the mass of this one, say we have 100 grams. So 100 grams of that compound, and we've determined that it's pure. That's important, it has to be pure. Then we say, suppose, and we analyze it and say A happens to be 30 grams. So B is 70 grams. Now, what Proust is saying is that this proportion for that compound, as long as you have that compound and no other, then that ratio, 30 grams to 70 grams, or 30% A and 70% B, will always be the same, no matter what the origin of the compound. Okay? Now, that's not to say that you couldn't have different combinations of A and B. You could have a different compound with 70% A and 30% B. That's possible. But as long as it's this compound and it's identified as that compound, it will always have that proportion. So that's definite proportion, the law of definite proportion. Example. There's water. If you identify water as a product of a reaction, it will always have the same ratio of hydrogen to oxygen, no matter what its origin. For instance, we could form water by reacting an acid and a base. It always produces water as one product. Or you could burn hydrogen in an oxygen atmosphere, and you get water as a product. It's always the same proportion of hydrogen to oxygen, whether it comes from an acid-base reaction or from a combustion. Doesn't matter. Okay, now here's one that can be confused with the law of definite proportions. This is John Dalton's law of multiple proportions. It sort of builds upon Proust's law of definite proportions, but it says that when you have two elements in a series of compounds, so you have I'm trying to think of a good example of a series of compounds. Okay, those are valid compounds of nitrogen and oxygen. Now what Dalton is saying is within that series where you have only nitrogen, only oxygen, the ratio of the mass of nitrogen to oxygen is always whole number. In other words, if you have so much of the compound where you can identify it as 1 gram of nitrogen in each one, then the amount of oxygen will be a certain amount here, but the next one will be twice that amount. And the third one will be 3 times that amount. What's happening is, at this time, for Proust and Dalton and others, they didn't know about the ratio of atom to atom. That concept had not been developed. All they knew was masses. They were working with masses, and that was it. So all these first laws are in terms of mass. So the mass ratio of this one to this one is a given value. But when you get to this one, it's a whole number multiple. So it's a proportion. If this is 1 to 1, then this would be 2 to 1, and this would be 3 to 1. Okay. That's what multiple proportions law means. Okay, so Dalton was pretty busy, and by the time the 19th century began, early 1800s, Dalton had gathered all this information together and was proposing a reason for these laws. Why do these laws work? Why are they solid? I mean, they always give you the same result. And he wanted to explain why. So Dalton came up with with his atomic theory, and he sort of borrowed the atomic concept from the ancient Greeks. The ancient Greeks believed that all matter was composed of a small particle, the smallest one, that couldn't be any smaller. And that's why they call it, the atom. Tomos in Greek means to cut. And a is a prefix that means not. It's the negative of. So whatever they were identifying as the smallest part, they were saying you can't cut it any smaller. That's where atom comes from. So Dalton borrowed that idea, but he took it one step further because the Greeks thought that all atoms were alike. Every atom was the same as every other atom. But Dalton realized that in order for his theory to be useful, he modified a little bit and said that each atom of every element is identical. So within the element, all the atoms are the same. But if you change to a different element, like we changed from hydrogen to oxygen, the atoms of oxygen are different than the atoms of hydrogen. Okay? So each element is made up of tiny particles called atoms. That's true. But the atoms of a given element are identical, and the atoms of one element are different than the atoms of another element in some fundamental way. He wasn't proposing why yet. It would take researchers a century or so to figure that out. What he was saying also was that chemical compounds, and they knew what compounds were. They weren't elements because by chemical means, you could break them apart and eventually end up with pure elements as a consequence. But compounds of two or more elements are composed of different atoms. And the way you get compounds is that you just combine atoms in different numbers, different arrangements of the atoms. That gave you different compounds and resulting properties. So a compound is basically two or more elements with different ratios. Each one of these compounds has entirely different properties. Okay, we could add to the list. Right? N2O, nitrous oxide. Everybody knows nitrous oxide. If you've ever been to the dentist, eventually you get to breathe a nitrous oxide. Okay, Dalton also said in his theory that when a chemical reaction occurs, and this is why the law of conservation of mass in a reaction, this is why it works. Because in a chemical reaction, you don't create atoms, you don't destroy atoms, you just rearrange them. So we use an arrow. So you have reactants on this side, products on that side. So when you have so many atoms of a particular element on this side combined in a compound, on this side, they're just reshuffled into one or more different compounds. So you don't change the atoms in the chemical reaction, and that's why the mass on this side is equal to the mass on that side. Because all you've done is play musical chairs with them. Okay. Then along comes, very shortly, after Dalton's theory, Gay-Lussac, who was another Frenchman, worked with gases. And gases were a useful entry-level means to investigate physical and chemical properties. And the main reason was that all gases, for some reason, tended to behave alike. You might have a gas, you might have hydrogen gas. It was fairly easy to produce. Or you might have carbon dioxide gas, which was easy to produce in the laboratory. And investigating either one of them under different conditions of temperature and pressure and volume they seemed to behave the same way. So it was convenient to investigate gases first. And that's what Gay-Lussac did. He measured the volume of gases as they reacted with one another. But he held the conditions of temperature and pressure constant. Well, when we get to gases, and we talk about gases, then I'll flesh this out a little more. But eventually, his work was built on by Avogadro, who was an Italian scientist. And what Avogadro says was, and this is important for chemical reactions, is that as long as you hold the temperature and pressure constant, then equal volumes of different gases contain the same number of particles. That was earth-shattering news. It seems so simple to us because we just take it for granted. But like I said, up to this point, scientists, chemists were dealing with masses only. And they were running into trouble with their chemical reactions because they didn't understand the microscopic level of a chemical reaction, what's going on underneath. Masses, that's macroscopic. You can even weigh a gas under the proper conditions. But they didn't understand what was going on at the microscopic level, and Avogadro's law gave them the clue to understand what was involved in a chemical reaction. It's actually atoms reacting with atoms. That in combination with Dalton's laws, Dalton's theory. So I'm going to save that for that further discussion of that one for the chapter on gases. Right now, we're just running through the history. Okay, so what Gay-Lussac observed was that if he had 2 volumes of hydrogen and 1 volume of oxygen, and remember they were at the same temperature and pressure, then he ended up with a reaction with products that occupied only 2 volumes of gas, water. So normally you would think arithmetic says 2 plus 1 is 3, but in chemistry, 2 plus 1 can be equal to 2. In this case, it's equal to 2. And when we learn how to balance equations, you'll see where that comes in. And the fact of the matter is, 2 volumes of hydrogen gives you a certain number of atoms, and 1 volume of oxygen gives you a certain number of oxygen atoms. When you combine them, then their combination gives you 2 volumes of water. So we're not actually adding oxygen and hydrogen here as we would arithmetically. We're adding them chemically, which gives us 2 volumes of gas. Now, occasionally, you do 1 plus 1 equals 2, like hydrogen and chlorine. 1 volume of that, 1 volume of that gives you 2 volumes of hydrogen chloride. But until we understand the atomic level of the reaction, we really don't know why this is true. If this was the only reaction that you'd ever studied, you might think that all chemistry is arithmetic. 1 plus 1 equals 2. But as soon as you try a different reaction, you find out that it ain't necessarily so. Now we know that the reason 2 volumes of hydrogen is because we've got 2 molecules of hydrogen. Each one has a hydrogen atom attached to another hydrogen atom. And 1 volume of oxygen has 2 oxygen atoms attached as 1 molecule. But when you combine them, you get 2 of the hydrogens attached to 1 oxygen. So you get one of these attached to those two and one of these attached to those two. So actually you're sort of shoehorning this one into that one volume, you're spreading this one out over that volume. And the reason you have two volumes is you have two molecules here. Here you have two volumes because you got two molecules, and here you got one molecule. Now, to measure that, you need lots of those molecules. Because we know that molecules are very small. So the key here is two molecules translates to two volumes, and one molecule translates to one volume, and here two molecules translates to two volumes. And this is why hydrogen and chlorine gas produce hydrogen chloride gas in an additive volume. Because here you have two molecules, there you only have one, there you only have one. Now on your periodic table that has the red boxes on it that I want you to learn, there are several of them, the elements, that have, I think they're blue. They're identified in blue. I don't have it on this chart, but they're gases, hydrogen here, and then nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are always diatomic. That is, the element at room temperature and pressure, 1 atmosphere pressure, will always have two atoms attached to one another. Okay. Those you need to memorize also, not just the symbol, but that one is always, when we say you are given a word problem, and it says hydrogen is reacted with chlorine, just like this one. You should know that in order to write the correct equation, you have to write H2 and Cl2. If I tell you it's hydrogen gas and chlorine gas, then you know that it's diatomic. So that's another, you have to memorize those as well. There's just a few of them, right? Hydrogen and then this inverted L, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are the diatomic elements. Okay. All right. So now we're going to, at the close of the 19th century and the beginning of the 20th century, scientists are going to start wondering, is the atom really the smallest particle of matter? And what they're discovering is that no, it's not. Now, once you go beneath the atom, into the atom and what it's made of, and if you break that apart, you don't have the element anymore. You only have the element if it has all of its constituent subatomic parts together. That's the element. But you can break it apart. And this is important because understanding the composition of an atom helps us understand why the elements are different, why the different atoms. So we're going to start with J.J. Thomson. And he was an Englishman. And he proposed that as part of the atoms of any element, there are negatively charged particles. And electricity was all the rage. Actually, it started way back in the late 16th century. Electricity was fascinating. In fact, it was entertainment at parties. People knew how to collect static charge on objects, and they actually built machines. They crank them up and get a huge static charge, and then the person that was holding on to the thing as it built up, they would have everybody down the line, everybody would hold hands, and then this one person would touch the outstretched hand of that long line, the conga line, and then everybody would jump because they get that jolt. So they knew about electricity way back. But now J.J. Thomson is saying, here's why the negative charge, because there are negatively charged particles as part of the atom. And he determined through his experimentation that we don't have time to go into right now, but he said the ratio of the mass of an electron to its charge is a given value. And he was right. Now the units of measure for the charge and the mass, of course the mass was pretty well established by now as the gram, but the charge was probably coulombs, which is not normally what we would think of as unitary charge for an electron. But be that as it may, the charge to mass ratio was determined by J.J. Thomson. And that begged the question. They knew that atoms were neutral, right? Atoms had no charge. They said, all right, if we're getting a negative charge out of an atom, there has to be positive charge in there to balance it of equal magnitude. Right? So there must be another particle in there somewhere that balances the charge for the atom. That's as far as they got at that point. They played with cathode ray tubes, right? And I won't go into detail about the construction here, but suffice it to say is the tube was evacuated because any air molecules in there would quench electrons very quickly. So the tube had to be evacuated. And they had then identified the source of electrons coming from this electrode. So they knew that they were traveling from that one to this one, and they played around with them to say, what effect would certain types of things have on that? So they had a positive negative charge built on either side, and they noticed that it deflected toward the positive charge. That was one confirmation that these electrons were negatively charged. And they also put strong magnets there, and they knew that certain particles, certain types of matter would bend in the magnetic field, and they confirmed that way also. Okay, so now along comes an American, Robert Millikan. He performed what's classically known as the oil drop experiment. And I got a little video following this that'll explain it better than I can in words. But basically what he determined by measuring this thousands of times, he did the same experiment over and over and over. It's called replication, only he took replication to the absurd and determined eventually the mass of the electron. So it's very, very small. Notice the kilogram is the fundamental unit in the metric system. And he determined that its mass of the electron was 10 to the minus 31st kilogram. Very, very small, very light. And this is how he did it. Ah, that's funny. Several measurements. How about thousands of measurements? The way I heard the story was you could suspend the drop, and he did it by looking at it through a telescope. So he could see the drop and made his adjustments so that the electric field, the strength was known. He also allowed droplets to fall in a field. And he used those two comparisons to determine the mass, because the mass would had a terminal velocity, and this is a vacuum chamber, so it had a terminal velocity in a magnetic field. And he used some complex mathematics and eventually determined the mass of the electron. Okay, so now about the same time, Henri, which is French, Becquerel, was investigating radioactivity. And radioactivity was a catch-all term for certain elements that would produce different types of, well, they didn't know in the beginning that they weren't all particles, but radiation. And how did they know about radiation? Well, they discovered purely by accident that certain elements would expose photographic plates. And they can do it through the light barriers that covered the plates. Right? Unexposed plate, of course, you'd have to keep it away from light or it would be exposed. So purely by accident was discovered that certain elements would expose the plate right through the material that covered it. So that sparked a revolution in scientific research on radioactivity. Eventually, three main types. There are lots of different types of radiation, but these are the main types. Gamma radiation, which is basically high energy light, very low frequency, high energy light beam, which originates from the nucleus of an atom. The other two are particles. Beta particles are nothing more than electrons that are moving at very high speed. And alpha particles, which are relatively heavy, have a 2+ charge, and they also originate from the nucleus. They also noticed that when these radiations were given off, changes were taking place in the element. In other words, one element was being transmuted into a different element as a consequence of emission of these radiations. Okay, so let's move on. Ernest Rutherford was confronted with the problem of how is the atom constructed. We knew that it had positive and negative parts to it. And one of the theories at the time was proposed by Lord Kelvin as the plum pudding model. Let's see, 2, 4, 6, 8, one more, there we go. The plum pudding model just said that positive and negatives were just mixed together in the atom. Like a plum pudding that had pieces of plum scattered throughout. Another one, the one that Rutherford believed was correct, was the nuclear atom. And the nuclear atom had most of its mass contained in a small nucleus, and then the electrons were in some sort of arrangement, orbits maybe, outside. So in order to prove the theory, he needed some way to bombard the atoms from outside and see what was the result. Right, so let's see. Well, I'm looking for his experiment. I thought it was, okay, I'll describe it. Let's see. Rutherford. So what Rutherford does did was take a very thin yet heavy element. Never guess which one it was. How about gold? Gold is one of those elements that you can hammer until it's very thin. 3, 4, half a dozen atoms thick, and it still holds together. That's why the dome in Charleston is covered with gold leaf they call it. It doesn't take much, just a few ounces. You just hammer it so thin that it spreads out over that whole dome. Actually, most of the cost of recoating the Charleston dome, the Capitol House dome, was labor, putting the stuff on. So he used gold because that way he could have a very thin, just a few atoms that would allow most of the radiation to pass through. So we have this gold foil. AU stands for gold. And then he has a source, and this is that's a lead barrier, and he has this source of radiation that emitted alpha radiation. He used alpha because they're really heavy particles, and he passed them through 2 slits called a collimator. The radiation coming out of here, the alpha particles coming out of here, could be like this, and if they come through here, they could go like that, they could go like that. See, so if you only have 1 slit, you could just get a scattered beam. He wants a collimated beam, a pencil-thin beam. So if you put 2 slits, line them up, then the only ones that can go straight through are the ones that are on a straight trajectory there. Okay, so now you got this straight trajectory, and then he had detectors all the way around. Film, right? Just film. And if the plum pudding model were accurate, then what you would expect is for most of the beam to end up right over here. It might spread out a little bit. But if his model was true, then you would still get most of the beam over here because most of the atom would be empty space. But occasionally, these alpha particles would strike the nucleus and be deflected. Even some of them would hit at such an angle that they would bounce almost straight back. Now, what were the results of his experiment? This one, the deflection part. So that disproved the plum pudding model and pretty much confirmed that the nuclear atom was correct. Okay. So I'm taking too long, of course. Okay, so with further investigations, one of Rutherford's students' name was Chadwick, worked on the mass of the atom, and they found that most of the mass was concentrated in the nucleus, and it was not negatively charged. Right? So the electrons carried almost nothing of the mass of an atom, and the protons were very heavy. But for some elements, they found, in fact, for most elements, they found that the mass didn't match up. Right? If you count the number of protons relative to the electrons, the mass didn't work. So they needed another particle that had no charge. And Chadwick worked on that one and found that there was evidence for neutrons, which are particles that are almost as heavy as the protons. Actually, they're heavier than the proton by just a little bit. and they're also located in the nucleus. So now we have electrons. So we identify an electron. Then we have protons. There's a symbol for the proton. And we have neutrons. Okay? So we have those three subatomic particles that are used to build an atom or an element, an atom of any element. Okay, so this is just give you an idea of the size of an atom, 10 to the minus 8 centimeters. So atoms are really small, but the nucleus is 5 orders of magnitude smaller. Right? So if this is the size of the atom, the nucleus is right here. So most of the atoms are empty space. In fact, all atoms are empty space. A large portion empty space. Now, I think these slides are out of order, so I'm gonna give you the some background so that we can talk about isotopes. When we write an element symbol, which you're learning now, I'm going to identify it as X because there are no elements on here that are just X. There's an Xe for xenon. That's it. So X is the element symbol. It can be anything. There are 4 positions around that element symbol that are reserved for certain types of information. Right? Up here is the charge. Charge always goes there, positive, negative, or neutral. Right? And if you want to specify neutral, you put a 0 there. If you don't put a 0 there, then it's assumed that it's neutral. Down here is how many. How many of them are we talking about? Right? So if we have gaseous hydrogen, there'll be an H with a sub 2 because the molecule is composed of 2 hydrogen atoms linked together. Over on this side, we have a position for the number of protons. So this is the number of atoms. This is the number of protons. And it's designated by a Z number. So this is the atomic number of the element. And up here, designated by an A, is the mass number. Okay? Now, how are they related? Well, these two are definitely related. The number of protons, or the atomic number, absolutely determines the element. For instance, hydrogen has an atomic number of 1. Nothing else has an atomic number of 1. If you have a different atomic number, you have a different element. Okay, so if you know the atomic number, you can find the element without fail. The mass number can be different for different isotopes of an element. And that's where the isotope comes in. The mass number is the number of protons plus the number of neutrons. Okay. So that's the mass number. So if you know the mass number and you know the number of protons, you can calculate the number of neutrons. And that's where isotopes come in. Every isotope of an element has the same atomic number, the same number of protons. So hydrogen can be this with a mass number of 1 because it has no neutrons, or it can be 2 where it has 1 neutron and 1 proton, or it can be 3 where it has 1 proton and 2 neutrons. Okay. This is called deuterium, and this is called tritium. And we can tell how many neutrons there are by subtracting 1 from 3. You can do that with any element. If you're given this one and that one, you can find out the number of neutrons. Or if it says, all right, this element has 5 neutrons. And let's say the element is boron. If I tell you it's boron, then you can look in your periodic table and say, okay, boron has to have 5 protons. Okay, 5 protons. All right, if it has 5 neutrons, then what is its mass number? 10. Just add them together. Okay. We'll talk about charge in a little bit. How do you get a charge? Well, we're on the subject. Let's just say, how do you know what the charge is? Well, the charge is an expression of the balance or the imbalance of protons and electrons. If you have the exact same number of protons and electrons, then the charge is 0. But if you have 1 extra electron, say you have 5 protons and 6 electrons, what's the charge? The charge is -1 or 1 minus, because you have an extra negative charge that's not balanced. But what if you have 5 protons and 4 electrons? Then your balance is toward the positive side. You have 1 extra proton that's not balanced by negatives. So in that case, it would be a 1 plus charge. Okay. So the moral of that story is you can only have a charge on an element by increasing or reducing the number of electrons. Why can't you do it with protons? Right? That would be in balance. Well, if you change the number of protons, you don't have the same element. Right? So you got to change the symbol too. So that's why when you're making, and we call them ions, when you're making an ion, you can only mess with the electrons. Leave the protons alone, unless you want a different element. All right. Okay, I'll make some more room here. All right. So that's an isotope. Same number of protons. This atom has the same number of protons as this atom. They have different number of neutrons. And all naturally occurring elements have a mix of isotopes. Some of them, a few rare ones, have almost equal numbers of 2 different isotopes. But most of them have, the vast majority are 1 isotope, and then they have minor amounts of the others. Okay, so here's an example of sodium. Sodium, 11 protons, mass number of 23, so how many neutrons? Subtract the 2, 12. For this sodium, subtract 11 from 24, and you've got 13 neutrons. So you know that they are isotopes of one another because they have different mass numbers, and they have consequently different numbers of neutrons. But it's still sodium because it has 11 protons. Okay? I explained this before, right? I got the slides right. Okay, let's try this. Say you have an isotope X with 23 protons. How would we write that? 23 protons, right? And 28 neutrons. What's the mass number? That's equal to your mass number, right? Just add the two together. What element is it? Well, we need our periodic table. 23 protons means, let's see, and they're small numbers to large numbers, top to bottom, and left to right. So you can just follow along till you find 23. And I think it's probably vanadium. So we have identified this as vanadium. All right, so let's talk about how do you make a molecule. You make a molecule by forming a bond between two atoms, okay? And there are different types of bonds that are possible. There are bonds where electrons are completely transferred from one atom to the other, which makes one positive and one negative. And then the attraction is purely electrostatic. They just now, of course, you'll notice right off that I didn't write the proper Cl2. We're just talking about two different atoms. So if I were going to write this in an equation, that would have to have a subscript of 2. But this is a sodium atom and a chlorine atom. Okay, so we'll find out as we go along that sodium is a metal, right? You know where sodium is. Pardon me for a moment. Okay. We'll find out that metals like to give up electrons and non-metals like to accept electrons. So what happens is one electron goes from here to there. Now you have a shortage. One electron short for sodium means a positive charge. Right? Because the imbalance is toward the positive if we lose one of the negatives. And we add a negative over here, right? Because that's where it went. Now you have electrostatic attraction, and this is an ionic bond, purely ionic. But what if you have two nonmetals and they have a more or less balanced attraction for an electron? There's a tug of war. One doesn't win. So there's an electron, or more than one electron actually, between the two elements that forms a bond. This is called a covalent bond. And this is where the electrons are shared between the two atoms. So let's stick with chlorine. So in the place of chlorine, since they have equal attractions for electrons, the electron from one is attracted to this one, and the electron from another one is attracted to that one. So we have two electrons in the middle. And that forms a covalent bond because they're sharing the electrons. Okay? So that's the general division of types of bonds, covalent versus ionic. And of course, you may already realize that there are gradations between the two. I mean, it's not a strictly ionic or strictly covalent. The bonding can have characteristics of either one. It's just in some cases, one dominates over the other. Now, when you have covalent bonding, you can actually call this is a molecule, because this grouping behaves as a single unit. Whereas with the sodium and the chlorine, the sodium and the chloride ion, they behave independently as ions, and they only attract one another, and they attract their neighbors. They do not behave as molecules. They behave as independent ions. So when we say molecule, you're always talking about a covalent bond.
Halogens will combine to form single bonds. Atoms
Okay. So here's the ionic bond that I was describing earlier. Oh, by the way, this positive ion is also called a cation. And the negative ion is called an anion. Just memorize it. There's no logic. There's probably some root to the word, but for now, just know the cations are positive and anions are negative. Okay. We're running out of time, and we're not gonna make it to the place where we need to talk about naming compounds. So because we can't shift to the next period, we don't have enough time, because this virus thing has cost us a whole week of school, of class time. I'm going to have to move ahead. So if you have to go, that's fine. And I'm going to continue discussing how to name compounds. And you can look at the video later if you have to go. Okay, that being said, let's carry on. A certain isotope has this formula, or that symbol. So it's an ion, it's a cation. It contains 54 electrons and 78 neutrons. Okay? What's the mass number of this isotope? Well, notice that it's an ion. So we need to find out how many protons are represented by that ion. So how do we get a positive charge out of an ion? We have an extra proton. Right, one extra proton, more than electrons. So if we have 54 electrons, that means we need 55 protons, right? And then we add that to the number of neutrons. Let's see, that's 12, 133. Okay. Yeah. So the mass number is 133. Didn't ask us what element it was, right? 55. Cesium. Okay. So which of the following statements regarding Dalton's atomic theory are still believed to be true? Right? Knowing what we know now about the subatomics, how many of these are still true? Can Dalton claim his theory is still true? Elements are made of tiny particles called atoms. Yep, they still are. All atoms are given of a given element are identical. No, they're not. Why are they not identical? Because of isotopes. Now, they behave chemically similar, very similar, but they're not identical because some elements, some atoms of the element have more neutrons than others, or fewer neutrons than others. How about the third one? A given compound always has the same relative number of types of atoms. That's true. Still true. Always will be true. And the last one, atoms are indestructible. We know that's not true because of nuclear reactions tear atoms apart all the time. We wouldn't have the atom bomb if it wasn't for that. So the only two that are true are the first one and the third one. Okay, let's look at the structure of the periodic table. I'm going to pull up this one right here. Okay, so metals versus non-metals, right? You're going to need to know this for your extra credit, right? Because the extra credit says you need to draw a line between the two groups, metals versus non-metals. And it goes right here between boron and aluminum. It goes like that, and it stair steps all the way down. That divides non-metals and metals. So most of the periodic table is metals, and there are just a few non-metals. How about groups or families, we used to call them? Those are the verticals. This is a family or a group. Periods. Periods are from left to right. Now, why do we call them periods? If you've ever, I don't know how many of you've had been exposed to physics, either in high school or in some other classes, but periodic motion is like the swinging of a pendulum. It's moving, yeah, but eventually it comes back to where it started from. That's one period. So the pendulum goes through one period through a swing, and you can think of that in terms of the elements. We go across a period and then can't go any farther. We've got to go down to the next row and start over again. That's a period. So you go back and start at a new position that's in the same group. So groups, periods, metals, non-metals. And here's an adjustment. Notice that hydrogen is all by its lonesome. Hydrogen is not a metal, but it made more sense to put hydrogen over here than it did over there. And it's just for balance. Okay, so what are some names of the various groups? Well, let's see. The first column are alkali metals. And the alkali metals, when they are charged, are always +1 charge. Always. In this first group. Second group, when they acquire a charge, they're always +2. So the first group is +1, the second group is +2, and they're called alkaline earth metals. We're going to skip the middles for now. We'll come back to them. And go all the way over to the other side. Over here on the far right are the noble gases. They're noble because they don't associate with commoners. They don't play well with anybody. They don't react. They are unreactive. And we'll find out eventually why that is. They don't acquire a charge at all. The halogens here, here we go, halogens, when they acquire a charge, they're always -1. It doesn't say here, but I'm going to give you the names. This family, or this group, is the chalcogens, C-H-A-L-C-O-G-E-N-S, chalcogens, the oxygen group. This family, or this group, is the pnictogens, starts with a P, P-N-I-C-T-O-G-E-N-S, pnictogens. Now, the one with carbon and boron at the top, they don't have family names. These in the middle are called transition metals. And for obvious reasons, they transition between this group and that group. And they can have variable charges. Some of them have numerous variable charges. This group down here, these are the lanthanides, because this row would normally be crammed right in here, just past lanthanum. They should go right in there. And the actinides would go right in here next to actinium. Why did we pull them out? Well, for one reason, as to keep our periodic table from being a mile wide. And for the other reason is, these have one thing in common, and we'll learn what that is when we investigate the electronic structure of elements. That's all I can say for now. I don't want to complicate things too much. But they're out there for a good reason. Okay, that's the basic overall structure of the periodic table. I've already told you these things. Now let's talk about naming compounds. And we're going to start with binary compounds. Binary means there are just two components. Now, for the most part, binary compounds are two elements combined together. But sometimes the position of one element can be assumed by a group of atoms we call polyatomic ions. Right? And you've got a whole list of those in a separate document that's in Blackboard. And it's also at the end of your review questions. The review document in the useful information has a whole list of those. And that's not by any means all of them, but those are the most common. Okay, so now that we know what a binary compound is, it can be either ionic or covalent. Right? So you're going to have two elements together. And we need some rules to go by. So we're going to start off with type 1. Type 1 compounds. They're always composed of a metal and a non-metal. Right? So, and the metal is always first in the formula of a compound. The metal, then followed by the non-metal. And for type 1 compounds, the metal always has a fixed charge. All right? So where can those metals come from? those metals can only come from alkali metals and alkaline earths. Because they're the only ones that have a fixed charge of either 1 or 2. Oh, one exception. The boron group. When these elements are in ionic compounds, they always have a +3 charge. So the first column is +1 charge, second is +2 charge, and this group is +3. Notice I skipped over the alkali metals. These are called, these 2 columns here and these 6 columns here are called representative elements. The representative elements are the ones that we have some fairly fixed ideas about, and the transition metals are the ones that are more variable. So we'll get back to those in just a second. So alkali metals, alkaline earths, and the boron family. So these are +1, +2, +3. Okay. Then the nonmetals can be anything in the nonmetal side. If they are halogens, they're always -1. If they're chalcogens, they're -2. If they're pnictogens, -3. Now this is for type 1 compounds, and these are always ionic. Now when you get over to carbon, all bets are off, because carbon can go either way, +4, -4, and anything in between. So I'm not going to give you a bunch of this type with carbon in it. Okay, so the type 1 compounds, let's see. Right. You name the metal first. We'll take an example. Sodium. Sodium is an alkali metal. It's a +1 charge. Chlorine is a halogen. It's a -1 charge. So notice, for neutral compounds like this, the charge is balanced. You only need 1 of each. That's important. You're not going to say 2 and 2. You're going to use the simplest whole number ratio, 1 and 1. +1, -1. Now, how do we name it? Well, the cation is always just the element name. And the anion is the element name with its ending changed to IDE. So, NaCl is the right formula, and the name is sodium chloride. Now, the overarching rule for all of these naming conventions, even for these simpler ones and for the more complex ones in organic chemistry, for instance, the overriding rule is non-ambiguity. What that means is, if you see that compound name, there's only one way to name it. Or if you see the name, there's only one way to write the formula. That's what I mean by non-ambiguity. You can't write 2 different formulas for the same name. Now, who decides? Right? Who gets to decide what the naming convention is? Well, that's a group, actually. And they go by this acronym. IUPAC. This stands for International Union of Pure and Applied Chemists. They make the decisions. They break the ties. Okay, so that's a type 1 compound. The cation element, the metal, is always fixed charge. There are no two ways about it. It can only have one charge. Okay, so now we have type 2. Type 2 compounds. Type 2s are also metal, non-metal. We'll come back to those examples in a minute. The type 2 compounds are always metal and non-metal, but the metal can have a variable charge. And that doesn't mean that once the compound is formed, the charge can change. That will. No, it means that when we form the compound, we could form it from a metal of a 2+ charge, or we could form it from a 3+ charge, or the different charges are available. But once the compound is formed, the charge is fixed for the compound. Okay, now, where do those metals come from? They come from the transitions. The transition metals supply us with multiple charges, plus a few down here. So transitions plus some of these guys. And that's why I also give you a periodic table with your review document, with your exams, that has possible charges listed. So you don't have to memorize the charges. Okay, so what are the rules here? Well, the rules are very similar, except when you write the compound name, you have to specify the charge on the metal. So let's take an example. Let's say I give you this formula, Fe for iron, and it's an ionic compound with 3 chlorines. So the simplest whole number ratio is 1 iron for every 3 chlorines in this compound. So we know that the chlorides are always -1. It's a halogen. Right? So this one is a -1 charge. So how many does that total represent? 3 minuses, right? 3 of them times -1 is 3 minuses. So how many positives does iron have to balance 3 minuses? Well, there's only 1 iron, so it has to take the whole brunt. So it has to be a 3+ charge, right, to balance these. All compounds are neutral. So now that we balance the charges and we see that this is how we deduce what is the charge on iron. So the charge on iron is 3+. Now we can write the name. So we say iron give the charge in a Roman numeral, chloride. And that's the name for that compound. Now that name, we can use that name to write the compound if we don't know it. So let's pick another one with the name and see if we can write the compound. Write the formula. Let's try this one. Okay? We have 2 chromium atoms and 3 oxygens. So if you look on your periodic table, you'll notice that the chalcogens are just next door to the halogens. The halogens are -1, oxygens Chalcogens are -2. So that means this is 2 minus charge. So how many total do we have? 3 times 2 is 6 minus, right? Okay. What do we need to balance 6 minus? We need 6 plus. So we need that many total charges from the cation. But there are 2 chromiums. So how much does each one represent? 2 into 6 is 3. So each one is 3 plus. Now we can name it. Chromium 3 oxide. And with that name, we can write that compound without missing it. Or, like we did here, we can take the compound and write the name. Non-ambiguous. Okay. There's some other examples.
To work out
Hold on a second.
the
Yeah. Okay, we're going to look at a little polyatomics. This is okay. We can do polyatomics. So what are some polyatomics? Well, some of the more common ones are hydroxide or, oops, my mistake, nitrate or sulfate. Notice these are all charged, but they're charged, that charge that for 2 minus on sulfate, for instance, that charge is distributed over the entire molecule, right? It's a polyatomic ion. In other words, you can't assign the charge to any one of these atoms. It's for the whole thing. So when we combine these in a compound, we need to know, is the cation or the metal a fixed charge or a variable charge? Then it would enter into the structure and the naming convention of either a type 1 or a type 2. The example there is sodium. Sodium is a fixed charge, so that's type 1. All you have to say is sodium hydroxide. That's it. Done. For this one, that's an alkali metal. It can only have 1 charge, and that's a 2 plus. It's in the second column. 2 plus. So in order to get balance minuses with pluses, we need 2 of these, don't we? But remember I said this charge is for the whole unit. So you can't mess with these subscripts. You have to go. You need 2 of the wholes to give you 2 minuses against 2 pluses. That's the one thing about polyatomics. You cannot mess with their subscripts. Those subscripts are determined beforehand, and that is the structure of the polyatomic ion. Now, there's only one polyatomic that we're interested in that has a positive charge. All of them are negative except for this one. That's ammonium. It's a positive 1 charge. It's always that way. And all your polyatomics are fixed charges. They don't change. So if we need 2 positives to go against 2 negatives, we need 2 of those. That's ammonium sulfate. Okay, so those are your polyatomics. Now we can move to
formula of an ionic compound.
Oh.
We first select a
Okay. Okay, here's another one. Suppose we form a compound with magnesium and phosphate. What's the charge on magnesium? It's in the second column, so it's a 2+ charge. Now, we've got an even and an odd. How do we resolve that one? Well, the simplest way is cross multiply. Take that 3 over here and take this 2 over there. And then check yourself, right? 2 times 3 minus is 6 minus. And 3 times 2 plus is 6 plus. We're balanced. Okay? All right. Let's see. Now, type 3 compounds. Type 3 compounds are composed of nonmetal and nonmetal. Okay, 2 nonmetals. And another characteristic of these compounds is they are always covalent bonds. So you don't have ions to deal with. So since you don't have ions to deal with, the name cation anion has no meaning. But we're going to steal from the ionic naming convention, the binary convention, to give us a leg up in naming these compounds. So we're going to have one first, and the second one is second. And as a general rule, the first one is going to be the one that's to the left, and the second one, the position of the anion, is going to be for the one to the right. That's not always the case, but most of the time it is. So you have 2 nonmetals, covalently bound, and we're going to name them as if they were cation anion. But since they are not charged, then the name is going to say how many there are of each one. And we use the Greek prefixes for numbers, 1 through 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is mono. This is di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Those are the prefixes that mean each of these numbers. And there should be a slide on it here in a minute, and it's in your book, of course. So let's take an example. One that's in the news a lot. How about this one? First of all, do we have 2 nonmetals? Well, we look over here. Yep. Carbon is to the right of the line. Oxygen is to the right. 2 nonmetals. That means it's type 3. So we say carbon. And notice if there's only one carbon in the cation position, we don't say mono. Mono never comes first. And then we have 2 oxygens, so it's dioxide. That's why carbon dioxide. Or if you get trapped in your garage and the engine of your car's running and you can't get out, what kills you? carbon monoxide. And notice, I don't say monooxide. Chemists are still sensitive about aesthetics, you know, things that sound right. So we don't say monooxide, we say monoxide. Just drop one of the O's. But this is, and you can write the compound from that name, 1 carbon, 1 oxygen. That's it. Okay. Let's see. Oh, there they are. Your prefixes. Okay, we got some more examples. There's carbon dioxide, sulfur. First, I'd look to see, are they both nonmetals? Yes, they are. Sulfur and fluorine are both nonmetals. So we're type 3. And we have 6 fluorines. So it's sulfur, hexafluoride. Now, if your first element is more than 1, you do give it the prefix that's required. So this one would be dinitrogen tetroxide. And for aesthetic purposes, we drop the A. We don't say tetraoxide, we say tetroxide. And here's a flow chart for naming compounds. If you like flow charts, fine. But I don't carry flow charts in my head. So if you're faced with a compound, either a name or a formula, then what's the first question you ask yourself regarding its nomenclature? Is it a metal, nonmetal, or is it 2 nonmetals? If it's a metal, nonmetal, then you're either a type 1 or a type 2. If it's a nonmetal, then you're type 3. Okay? So if you're over here, you know all you have to do is give it prefixes for the numbers. If you're over here, then you have to make another decision. Is the metal fixed charge or variable charge? If it's fixed charge, you're type 1. Variable charge, type 2. And if it's variable charge, then when you actually write the name of the compound, you have to write the charge behind the cation in Roman numerals. And that's it. That's the whole nomenclature in one ball of wax, at least for inorganic chemistry. If you have designs on organic chemistry, then we have another set of rules. So that's your choice. Okay. Let's see. Now we have naming conventions for acids and bases. And the reason we have naming conventions for acids and bases is because they predate modern chemistry. So we're sort of stuck with them. And the best we could do is form some rules around their names to standardize things. So what are the characteristics of an acid? Right? When you see a formula for an acid, it's always going to have start with a hydrogen or one or more hydrogens. And then it will be followed by some anion, either an anion of an element or a polyatomic anion, one or the other. Now, this hydrogen, this first hydrogen, or 2 or 3 or however many there are, those are the hydrogens that when you put this compound in water, these dissociate and become protons. That's where the acidity comes from. For instance, If you just have that compound and it's free, it will be a gas. And this is hydrogen chloride. But if you put it in water, G is for gas, AQ is aqueous for water, L is for liquid, and S is for solid. So if you put that in water, now you have the potential for dissociating that hydrogen into its environment and producing an acidic solution. That's when the naming convention kicks in for acids. Okay? All right, so what's the rule? First rule. Are there oxygens in the anion? Are there any oxygens in the non-hydrogen part of the molecule? Right? In these examples, there are no oxygens out there, right? So if that's the case, you always start the name with hydro. Hydro something. Then you fill in the rest of the molecule depending on what that something is. If it's chlorine, ides become X. So chloride becomes chloric. Hydrochloric would be HCl, hydrochloric acid. And I'm leaving off the aqueous because we're talking about acids all the way down now. Here's another one. Cn is a polyatomic ion, and it's called cyanide, the cyanide ion. Ide becomes ic, so now it's cyanic. Hydrocyanic acid is HCN. If we just have sulfur, sulfide, hydrogen sulfide dissolved in water becomes hydro. And here comes some aesthetics again. Hydrosulfuric. It's not hydrosulfic, it's hydrosulfuric. So that's what happens if you don't have oxygen in the molecule. Now, of course, you're probably wondering, what do you do if you do? Well, how do you name one with oxygen? Okay. So is there oxygen in the anion? So if there is oxygen in the anion, you drop the hydro. No. Hydro. You don't say hydro. If there's oxygen in there, you just take the anion, and it's going to be a polyatomic, obviously. You take the polyatomic ion and you change the 8 ending to ic. So in this case, NO3 minus is nitrate ion. So it becomes HNO3 is nitric acid. Okay, 8s become X. Sulfate becomes sulfuric. C2H3O2 is acetate. becomes acetic. And everybody knows acetic acid. 5% acetic acid is vinegar. Okay, so let's continue with oxygens. So if H's become X, okay, then what if you have a polyatomic that ends in ITE? We do have some like that. So we have sulfate and we have sulfite. Ites become us. So instead of SO3 2 minus becomes H2SO3. That's sulfurous. Sulfur. Sulfurous acid. Okay? H's become X, I's become us's. Examples. Okay, let's see. Let me go back. You'll notice that we can make acids of almost any of the polyatomic ions because all but one of them is anion. And you'll notice that some of them occur in groups, like families. This may help you remember them. Okay, one of the biggest families is made of halogens, right? So we'll have one that's like this, and that is chlorate. That's the chlorate ion. Then if you take away an oxygen, you have the chlorite anion. If you take away another one, notice the charge stays the same, but we just lose some oxygen. Then we don't have any more suffixes available, so we have to add a prefix. So we go underneath the ite, hypo, like hypodermic under the skin. We go underneath the ite. So we go hypo chlorite. Okay. Then we can go one more oxygen this direction. And we don't have any more endings for adding an oxygen, so we add a prefix, and that prefix is per. Okay, so there's a family, and all we did was change the oxygens. So I always start with this one: chlorate, chlorite, hypochlorite, and perchlorate. Now, what do you do when you make an acid out of them? Well, you add a hydrogen to each one because the hydrogen has a positive charge, and a positive plus a negative is neutral. Okay? Now we have our acids. How do we name them? Well, this one's easy, right? We did that one already. So this is chloric acid. This one is chlorous acid. So what does that make this one? Well, ITE, we can keep that as us, but we have to keep the hypo. So we say hypochlorous acid. And then this one is perchloric acid. Okay? So there's a method And you can do this with any of the halogens. Well, you can do it with chlorine, you can do it with bromine, and you can do it with iodine. Just substitute one in here, and the name just substitutes here. Instead of per chloric acid, it's per bromic acid or per iodic acid. So with just that one sequence, you can get 12 different acids, all halogen acids. You can't do it with fluorine. Fluorine's a halogen, but it doesn't form these compounds. They're not stable. Oxides of fluorine are not stable. So you only have those three to deal with. Okay. So that's naming compounds. Let's see, is there any more? Just samples, examples here. And plus you have the extra credit, that 50 question extra credit for naming compounds. Let me see. Hold on a second. I've covered most of the rules, but I want to see if there are any minor rules that I've missed. Okay, we did that one, that one. You'll need to have your polyatomic ion list with you when you do this, of course. And you'll have it available during the exam, because anything that's part of the review document in that useful information section at the end is reproduced for the exam. So you always have that information. Here's a naming convention we didn't cover, and that is waters of hydration. We have a lab that we do that for, but for naming the compounds, we haven't got to it yet. So what do you do if you've got a compound that has waters loosely attached to them? Waters of hydration. Perfect example. Right? That's a sulfate anion. That's calcium. Calcium is an alkali metal, so it has a 2+ charge. Sulfate is a polyatomic ion with a 2- charge. So one of these and one of those together, neutral. Right? That's calcium sulfate. But if you expose calcium sulfate to the air, it will absorb water and produce a compound we commonly call gypsum. So everybody knows about gypsum board, stuff that your walls are made out of. That's what it is right there. And it's made by adding 2 water molecules attached to the calcium sulfate in the crystal structure. Right? And this is how we denote 2 waters with calcium sulfate. We put that dot in the middle of the line, and then the number of waters. So how do you name it? Well, you name this part first. Calcium sulfate. And then you say, how many hydrates? So hydrate means water. So we have dihydrate. Okay? And with that name, you can also write this one, because you know this is the ionic compound and this is the water attached to it. Okay, so you will need that to answer some of these. Let's see if I missed any others. How do you recognize a polyatomic ion when you see it in a compound? Well, there are clues. These are not hard and fast, but there are clues. Most of them have, if you have 3 or more elements, and one of them is oxygen, then you probably have a polyatomic and you need to get out your list and look to see if it's there. There are a few exceptions, right? Hydroxyl, yeah, it has oxygen. Sulfate's got oxygen. Phosphate's got oxygen. That one doesn't have. So you might just have to memorize that one, or just recognize it when you see it. That's a polyatomic. Let's see. Okay, I think that gives you everything you need to know to fill out the extra credit. All right. Okay, I believe this is the end of it. Yep. Okay, so I only went 45 minutes or almost 50 minutes over, which is pretty good for me, actually. All right, any questions? Let me stop share. There we go. We're still recording. That's good. And Thursday, we'll have a review session. So we'll take, what I usually do is take that review document that I showed you that had the key with it, and it had my worked problems also in a separate document. I usually take that one and we use that as our guide. If any of those problems that you've worked there give you trouble, then I open the floor first to let you offer those problems, and we solve those first, so that if we run along, then I don't miss out getting questions answered that are bothering you. And then the rest of the time, I'll just fill it in with what I think is important. And then I guess that makes the following Tuesday, 2 weeks from today, will be our first exam. And let me see. Let me just check my schedule and be sure. Oh, no. Okay. My mistake. Well, no, let's see. We got a buffer day built in. Thursday's a buffer day. So I could have let this one go till Thursday. Well, we can use Thursday for a little bit of review. Then we could do part of the lab on them. In case some people aren't able to come back in the afternoon on Thursday for the lab, then we can work on that Thursday as well. But the exam is on Thursday the 10th, or at least no later than. Since you're going to have, you do the exam on your own and turn it in on Blackboard, then what we'll do is we'll jump right in on that Thursday in Chapter 3. So by the time we get to that point, you should have already completed the first exam and ready to go with the next one. Okay, now any questions? We're all good? Okay. We'll see you Thursday.
Sorry, I do have a.
Yeah, sure. Is that Jackie talking?
Now, yes. With the
Okay.
OWL, I got your email saying if you haven't started, your assignments, jump on them. Now, is the assignments you're talking about the OWL ones, the OWL Cengage?
Yeah, you should. The Cengage gives you a 14-day grace period from the beginning of the semester. So you can register with them even without buying unlimited in case your financial support is lagging. And then when the financial support... Yeah, go ahead.
Sorry.
I'm
I
listening.
do have Cengage, and I just was confused on the assignments. Like OWL popped up, and when you click on Cengage, it takes you to OWL. And then if you click on all assignments, they have practice and then graded.
Right, the ones that are
I was
graded
just
are
confused
identified.
on which one.
Yeah, the ones that are graded are identified as such. Also, this would be a good, let me share, let's see. Let me share, let's see, not that one. Let me share. I think it's this one. Yeah, okay, so let's go into Blackboard. And then find the course. Bottom, and then be this one. And then let me make it look like student view. Okay, there we go. So now if you go into start here, I had this link here. This takes you to Cengage the first time so that you can get set up and registered. But every time after that, if you don't want to be bothered with having to look around for what homework assignments are due, go into each of the exam folders. So exam 1, and then there's a homework link here for chapter 1 and chapter 2. And that way, you're not bothered with having to search for which one's the right one. As soon as it loads up.
I get it. Yeah, just complete the ones, like if you go over chapter 1 by the end of the week, do that one.
Okay. Since I'm an instructor, it's not gonna do it, but yours should pop up in that assignment when you do it that way. Now, if you want to work any of those extra practice problems or other types that are not graded, then you can use that first link that you use to register. And then you have access to everything all at once. But the reason I put those in is so try to help with possible confusion and keep you on track with the assignments that are actually graded.
Okay, I understand now. I was looking at the full list of OWL, the full list, and was
right. Yes, and if this is the first time that you've ever done a Zoom class or a fully web-based class, it can be. It puts a lot of work on the student's shoulder. I understand that. So that's why those deadlines are more suggestions. To stay up and current with all the activities that we're doing, you should try to stay with the deadlines. But if you turn them in late, I'm not going to penalize you for them.
I understand. Thank you.
All righty. Anybody else have some problems? No? Okay. Well, we're an hour over, and I think that's probably long enough. So We'll see you again on Thursday. Unless you want to pop in on my office hours, that's fine too. So long. I'm going to stop the recording here.